Imagine a world where the past isn't set in stone, where every moment is fluid and malleable, where echoes of the future could reach back, subtly shaping the events that came before, creating a tapestry of time that is ever-changing and dynamic. This is the perplexing realm of retrocausality, a concept that challenges our fundamental understanding of time and reality. It suggests that the future can influence the past, creating a loop of cause and effect that defies our conventional logic. Can the future truly influence the past? This question has puzzled scientists and philosophers alike for centuries. The very notion seems paradoxical, a violation of the natural order. Yet it opens up a realm of possibilities that are as fascinating as they are bewildering. Our intuition tells us that time flows in one direction from the past through the present and into the future. This linear progression is what we experience in our daily lives. This is the arrow of time, an unwavering constant in our everyday experience. It is the framework within which we understand our existence and the world around us. Yet, at the fringes of physics, where the laws of the universe are pushed to their limits, a different picture begins to emerge. Here, the boundaries of time and space are not so rigid. In the realm of quantum mechanics and the mind-bending theories of relativity, the neat lines between cause and effect begin to blur. Particles can exist in multiple states at once, and events can be interconnected in ways that defy our traditional understanding. The future, it seems, is not so easily separated from the past. They are intertwined in a complex dance, each influencing the other in ways we are only beginning to comprehend. It is a realm of tantalizing possibilities where our understanding of the cosmos is tested and reshaped. As we delve deeper into the mysteries of time, we may find that the past, present and future are not distinct entities, but rather threads in a single, intricate tapestry. The exploration of retrocausality invites us to rethink our place in the universe, to consider the profound implications of a world where time is not a straight line, but a complex web of interconnections. As we stand on the brink of new discoveries, we are reminded that the universe is far more mysterious and wondrous than we can imagine. The ripple in time is just the beginning of a journey into the unknown. From our earliest memories, we experience time as a linear progression. We see it in the way we grow, the way seasons change, and the way day turns into night. Time to us is a constant march forward, a journey that we all embark upon from the moment we are born. The past is fixed, immutable. It is a collection of moments that have already happened, etched into the fabric of history. We can look back at old photographs, visit ancient ruins, and read historical documents to glimpse what once was. But we cannot change it. The present is what we perceive now, fleeting and ever-changing. It is the moment we are currently experiencing, the here and now. As we go about our daily lives, the present is constantly slipping through our fingers, turning into the past with every tick of the clock. The future remains unwritten, a canvas of possibilities waiting to unfold. It is the realm of potential where anything can happen. We make plans, set goals, and dream about what the future might hold, but it is always just out of reach, waiting to be shaped by our actions. This intuitive understanding is reinforced by the classical laws of physics, which govern the motion of planets, the swing of pendulums, and the trajectory of a ball thrown high into the air. These laws provide a framework for understanding the physical world, giving us a sense of order and predictability. When we see a ball thrown into the air, we know it will follow a certain path and eventually come back down. This predictability is comforting, a reminder that some things in life follow a set pattern. These laws work equally well whether time moves forward or backward. In theory, if we were to reverse the direction of time, the same physical laws would apply. However, our everyday experience tells us that time only moves in one direction. Yet there is a fundamental asymmetry to time that these laws fail to capture. This asymmetry is evident in the way certain processes unfold, always moving towards greater disorder. This is the thermodynamic arrow of time, dictated by the relentless increase of entropy, a measure of disorder in the universe. As time progresses, systems naturally evolve from states of lower entropy to states of higher entropy. Imagine a drop of ink spreading through a glass of water. Initially, the ink is concentrated in one spot, but over time it disperses throughout the water, creating a more disordered state. We instinctively know that the ink will disperse, becoming increasingly disordered over time. This natural tendency towards disorder is a hallmark of the thermodynamic arrow of time. This process is irreversible, marking the passage of time in one direction. Once the ink has dispersed, it cannot spontaneously gather back into its original drop. This irreversibility is a key feature of the arrow of time. But what if this arrow of time, this seemingly fundamental aspect of reality, is not as steadfast as we believe? Could there be conditions or realms where the arrow of time behaves differently or even reverses? These questions challenge our understanding and invite us to explore the deeper mysteries of time itself. In the early 20th century, Albert Einstein revolutionized our understanding of time with his groundbreaking theory of relativity. Time, he revealed, was not absolute but relative, dependent on the observer's unique frame of reference. Imagine two observers, one standing still on Earth, the other traveling at near the speed of light. Einstein's theory predicts that time will pass more slowly for the moving observer relative to the stationary one. This phenomenon, known as time dilation, has been experimentally verified and has profound implications for our understanding of the cosmos. Einstein's theory also unified space and time into a single fabric, space-time. This fabric, he proposed, is warped and curved by the presence of mass and energy, much like a bowling ball placed on a trampoline. This curvature of space-time is what we experience as gravity. But Einstein's theories went further, hinting at the possibility of wormholes, theoretical tunnels that connect different points in space-time. These shortcuts could potentially allow for travel through time, both forward and backward. While Einstein's theories revolutionized our understanding of the large-scale universe, they were not the final word on the nature of reality. Another revolution was brewing in the realm of the very small, the world of atoms and subatomic particles. This microscopic domain held secrets that would challenge and expand our understanding of the universe. This was the birth of quantum mechanics, a theory that challenged the deterministic worldview of classical physics. Pioneers like Niels Bohr, Werner Heisenberg and Erwin Schrödinger delved into the mysteries of the quantum world, uncovering phenomena that defied conventional logic. Quantum mechanics revealed a world of inherent uncertainty and probability. Unlike the predictable orbits of planets, particles at the quantum level behaved in ways that could only be described by probabilities. Particles, it seemed, did not follow predictable paths but existed in a haze of possibilities, their exact locations and velocities unknowable until measured. This probabilistic nature was a stark contrast to the deterministic laws that governed the macroscopic world. Their behavior governed by chance, quantum particles introduced a level of randomness into the fabric of reality. This randomness was not due to any lack of knowledge or precision in measurement, but was a fundamental aspect of nature itself. Measuring one property of a particle, such as its position, inherently affected its momentum and vice versa. This interplay between position and momentum was encapsulated in Heisenberg's uncertainty principle, which stated that the more precisely one property was measured, the less precisely the other could be known. This fundamental uncertainty, known as Heisenberg's uncertainty principle, shook the foundations of classical physics. It suggested that at a fundamental level the universe was not a clockwork mechanism, but a dynamic and unpredictable system. Even more perplexing was the concept of quantum entanglement. When particles became entangled, their properties became linked in such a way that the state of one particle was instantly connected to the state of another, no matter the distance between them. Two entangled particles, even separated by vast distances, remained mysteriously connected. This connection was instantaneous, defying the classical notion that information could not travel faster than the speed of light. Measuring the state of one instantly determined the state of the other, regardless of the distance between them. This phenomenon baffled even Einstein, who referred to it as spooky action at a distance. This spooky action at a distance, as Einstein famously called it, seemed to defy the limits of causality. It suggested that the universe was interconnected in ways that classical physics could not explain. Could these strange properties of the quantum world hold the key to understanding retrocausality? Retrocausality is the idea that the future can influence the past, a concept that challenges our conventional understanding of time. Might the interconnectedness of quantum entanglement allow for influences to travel backward in time? If so, it could open up new realms of possibility, where the boundaries of time and space are not as rigid as we once thought.